My name is Jakob Foerster, and it's my great honor and pleasure to be here. Thank you all for being here. In the next 50 minutes or so, I'd like to tell you a little bit about where I would like to take the work that I've done in the last few years. Because I think we are experiencing a paradigm shift right now, whereby it's simply no longer appropriate to think of our machine learning systems as existing in vacuum. In recent years, what we've seen of the progress has been in supervised learning, where we have a static data set of inputs and expected desired outputs, X and Y. Think of machine translation, of image recognition, and so on and so forth. And typically, we've ignored the fact that the world contains other agents. Those other agents might be the human users of the system, but they might also be other machine learning systems that exist in the same environment. And I believe we have to start recognizing that those agents are different from other parts of the environment. Agents are special. Agents have beliefs, they have points of views, and they have intentions. Right now, when you're looking at me, you're trying to figure out what is he trying to say, right? This is such a deeply human thing to do, reasoning over the intentions of another being. And I think in the future, as we're deploying more machine learning systems in the real world, we have to start thinking about the context of agency in the era of learning systems. What does it mean for a learning system to be in an environment when there are other intelligent agents? Now, a natural starting place for this kind of journey is to think about multi-agent systems. It doesn't matter whether you think about communication networks, as shown on the top left, you think about the Internet of Things, drones in the sky, or robots in the warehouse. In all of these examples, we have a large number of agents that are taking decentralized actions based on local observations. So, for example, these drones may have to coordinate, but each drone can only see some small spot of the total surface. And they have to carry out some overall objective. That's a multi-agent problem. What's interesting here in this system is that we can control all of the different drones. So while it is multiple agents interacting, we have total access to the policies, update rules, observations of all these agents, which makes for a great testbed for exploring the ideas of agency in the context of learning systems. Furthermore, because we have this ground truth access, we can also carry out centralized training using decentralized execution. So while we're trying to find the policies, we're typically using learning methods here. We can run learning algorithms in a centralized fashion on a simulator where we have ground truth access to all the policies involved, as long as these policies we're finding learning can be deployed in the real world. And obviously, at execution time, each drone can only see that patch of land that they can look at during their trajectory. Right? So that's this paradigm of centralized training and decentralized execution, which is sort of a stepping stone. It allows us to break down some of the challenges associated with multi-agent systems during training time, as long as we can execute it later on. But I think these ideas of agency extend much beyond that multi-agent, that typical multi-agent context. Think, for example, about self-driving cars. When humans are in traffic and you're approaching a lane merger, humans, by default, will find a way to coordinate. They sometimes establish eye contact. They acknowledge that another agent is there. They reason over the point of view and the beliefs and likely intentions of that other human driver. Our self-driving cars so far do not have these abilities. In fact, Waymo recently stated that they have to start modeling other traffic participants, which they claim is a rich area of ongoing research. This deficiency of thinking over other agents in the environment in the context of our learning systems can be observed right now on the road. This is a report by the Arizona Times, which noticed that these cars sometimes took 1.5 minutes, even in moderately flowing traffic, to carry out lane mergers. Now, this seems like a drastic failure, but can also be a source of amusement. So this is a Twitter user that posted a video of this Waymo car trying to merge onto the highway. And it indicated multiple times, say, I do want to merge. And the person was filming it. But ultimately, even though there's obviously space on the road, this car failed to merge and ended up exiting the highway on a different exit. Now let's think about this, what's going on here. First of all, the car failed in this instance. But now let's think about learning systems and learning agents. What did the humans just learn in this setting? They just learned that indicating, when the Waymo car indicates, doesn't actually mean it's going to merge. So we're also, at the same time, diluting the signaling abilities of the Waymo cars. So we're actually observing something in real time here, which is a failure, not just in the situation, but conditioning humans to no longer take the signaling from the Waymo car seriously. And we'll get into this. What does the message actually mean? I have to know the intent of the agent. And we've broken this protocol in this setting. There's other settings where this agency is relevant. So imagine you're selling books on Amazon. And because you're extremely efficient, you're going to compete on price. You want your books to be listed at the top, so you're simply going to undercut the previous seller by 0.1%. So every day you look, what's the cheapest price? I'm going to undercut it by 0.1%. There's also a counterpart of yours, somebody who's got great customer service, great reviews, and they're going to upmark the prices of the most expensive offer by 27%. Now, both of these seem like perfectly reasonable strategies, assuming that the other prices are more or less static and that the environment is a given. It's not responding to you in any way or form. Now, can anyone guess the next slide? Something drastic is going to happen here on the next slide. And this is what happens, a drastic failure case when we forget that there's other agents that are also smart decision makers. It happens when these two sellers are the only ones selling a given book on flight genomics. This is an exponential curve. This is real data. Every day, the price was increasing by 27%. Until finally, this book was the most expensive book being sold on the planet for $23 million, when somebody finally stepped in and said, well, maybe this isn't quite the right price. We should set for the second-hand book. I'm sure it's great, but it's maybe not that fantastic. So we've seen that agency can matter in multi-agent systems, in self-driving cars, and in markets. How about the standard supervised learning problems? Let's look at Google Translate. Static data set, pairs of samples, X and Y, map from one to the other, that's it, you're done. Where's the agency? Well, the agency happens on the right-hand side. We have users. Now, those users go to your website, and what might they do with your translations? One thing that people like to do is build websites. So people have gone and used Google Translate to translate their websites into another language. What happens next? Google likes to get training data by scraping the internet. So immediately, we run into this daunting new challenge, citing here a research paper from Google Translate in 2010, where the human-generated data gets contaminated with their own outputs. Now, what you don't want to do in this world, you don't want to train on your own outputs, because that will propagate your own mistakes forever, right? So what we've seen now is agency comes up as a topic, even in those supervised learning problems. So in a lot of machine learning settings, we have to think about this. But how can we start thinking about agency in learning systems? A good starting point is reinforcement learning, right? Reinforcement learning is a framework which typically assumes a static environment on the right-hand side. We have this agent. The agent perceives the observation, the reward from the environment, and takes an action. Next, the environment undergoes a state transition, where a new state is sampled, which is conditioned here on the action taken by the agent and the previous state. The goal of this agent is to maximize the total expected return, which is nothing but the sum over rewards. Now, if you wonder what this gamma is, that's just discounting. It says we care more about things that happen immediately than things that happen in the future. What's important, this agent can interact with the environment over and over again to learn the optimal policy. And that is because the environment is static. We'll be using deep reinforcement learning in this talk as our go-to method because in principle, I want to be able to deploy these things in the real world at some point, where we have high-dimensional inputs mapping into policies and value functions. These agents are parameterized by deep neural networks. What is that? Well, I heard it's basically a large lookup table that's softly parameterized, but you can think of it as a function approximator that can be trained efficiently using backpropagation. The weights are indicated by theta, so everything that this agent does comes down to those weights theta that map from observations into policies. Because we're interested in agency, we'll not just be looking at one agent. Instead, we have an environment that contains a large number of different agents that each observe their own rewards, observations, and take their own actions. What makes this complicated is that the next state in this environment, the S prime that gets sampled from distribution, doesn't just condition on the action of the red agent, it conditions on the actions of all of these agents. Right? Now there is something you could do, and that is you could pretend that the other agents are just part of your environment. That's indicated here. We have a new world which contains all other agents. And this red agent is now ignoring the presence of those. Pretty much what Waymo is doing right now. Let's just ignore what that Amazon seller was doing. Let's ignore the agency of others. Right? I call this naive learning because we're ignoring the agency of everybody else. That creates issues because now the world is no longer static. I can't just interact over and over again. The way that I interact will change the learning of others. What you could also do is you could try and model the presence of other agents. Because they're changing, I want to be aware of what's happening in this world. So here, for example, the red agent is modeling the presence of all other agents, and the blue agents are doing the same. Now, if you think about it, the fact that I have a model of you clearly changes the way that I act. So you should probably model the fact that I have a model of you, and so should everybody else. Right? And we can see that if this was a difficult problem in the beginning, now clearly it's a much harder problem because you have these models of models of models. That's what happens, right? An explosion of complexity. And if this sounds a bit abstract, I'll show you a very specific case where this happens. We did a paper on learning with opponent learning awareness, which tries to move away from naive learning. This was published at AMAS in 2018. And essentially what we're doing is we have this Lola agent that models the opponent as a naive learner. So now no longer is the rest of the world static. There's a learning agent that's going to pursue their own objective. Importantly, my policy changes my reward, but also changes your learning behavior, which is impact on my reward. And this leads to fantastic things happening. So for example, agents now learn to reciprocate. They learn to reward and punish their opponents. They learn tit for tat in the iterative prisoner's dilemma. That's great. But let's look at it. It's a bit broken because when question.
So I just had a question. How does this relate to sort of game theory, which is sort of the general theory of this, at least that I learned a long time ago?
Yeah, so game theory is essentially saying if everyone plays optimally, right, then there are these stable equilibria. So there's a Nash equilibrium here, whereby if everyone plays this, we're done. The problem is how are you going to pick a Nash strategy for driving? Right? We don't exist in equilibrium. We exist in a world of learning and updating agent. No one is at equilibrium. And game theory tells you very, very little about strategies and learning behavior away from equilibrium. So we can't solve these games. The real world is too complicated to solve for the Nash equilibrium. In other words of saying this. Right? You can't solve Google Translate by thinking about Nash strategies. So we're trying to develop methods rather than solving games, which you can do in these simplest cases that game theory can address. We're trying to develop methods that can be deployed in principle in the real world, where we do have to rely on learning, right? We have to rely on samples from the environment, on experiences, and updating our policy. There's a fantastic question, by the way. So here, once again, these agents don't have access to the true value function. They don't know how to solve the game because they can't, because it's too complicated. And they have to rely on learning. They have to interact with the environment and take gradient steps to maximize the reward. Now we can account for the fact that the other agent is also is a learning agent, and we can now learn it for that. But let's think about this a little bit. This is really broken because I'm modeling my opponent as a naive learner. That's ignoring my presence. Right? That guy up there is ignoring my presence. What if two Lola agents meet? Well, clearly, I should model the opponent as a Lola agent. But then I'm trying to shape the learning mechanics of somebody who's trying to shape me. That's a second order Lola agent. Right? So immediately, it's again wrong. Right? So immediately you get to this explosion. So this we'll see over and over, yes?
So does this process converge under some conditions to some sort of fixed point?
You just jumped ahead in my talk to the future work section. Thank you very much. No, I appreciate it. Okay. Well, if you have an idea, I'd love to hear that. Good. So this was sort of high-level motivation. I hope I could convince you a little bit that we can't easily solve for Nash. And even if you could, outside 2 player 0 sum, Nash equilibria aren't that meaningful. Really, that's another thing I should have said earlier. Right? It doesn't help me. So in communication, for example, there's a vast number of Nash equilibria. We'll get to that in a little bit. I'll be talking about the ability of learning communication protocols, because I think that's key, not just to coordination amongst drones and so on, but it's also key and important for human life. Humans spend 50 to 80% of their time communicating at work. And clearly, future AI systems will have to communicate, not just amongst themselves, but also with humans in the environment. To understand why this is a hard problem, let's imagine a very simplistic game. I have a sender on the left and a recipient on the right. If you're communicating, you need those 2 components. One of the great challenges of AI research has been credit assignment. Imagine you're playing a chess game, and after 2 hours, you win the game. First of all, well done, that's fantastic. But secondly, because you want to learn from your experience, you have to figure out what move of yours caused this final outcome. How can I attribute the credit over time? And this is where Richard Bellman made a lot of progress, using this idea of TD learning and the Bellman equation. Essentially, we're comparing what happened after I took this action to what happens normally when I am in this state. So think of a specific state in the game, I can now think about this. That attributes the credit to that specific action. That's how we do reinforcement learning. in this chaotic situation of the Super Bowl, the same problem happens between different agents. All the different agents are taking actions over time, and now have to figure out who attributed what to the final outcome of the game. I mean, first of all, we know that the Patriots win. That always happens. But the interesting question is, who attributed what in this scenario? And this makes learning communication protocols so hard, because it's not enough for the sender to send the right messages. The recipient also has to understand the messages. So if I'm randomly exploring in the space of possible messages, and you're randomly doing something else, nothing happens, right? So in some sense, this isn't about credit assignment, but about blame assignment. When things are broken, I don't know if I'm doing the wrong thing or if you're not listening. This is, by the way, called the bubbling equilibrium in this area of research, whereby the sender is sending nonsense, the receiver isn't listening, and there's no incentive for either side to change. It also happens sometimes at cocktail hours. And only here, when everyone's doing the right thing, do we get rewards. We address this problem in our NURBS 2016 paper, Learn to Communicate with Deep Multi-Agent Reinforcement Learning. This paper at the time was well received by the community, and now there's a whole range of follow-up research in this area of emergent communication. And actually, there's a workshop every year that takes place addressing this question on emergent communication. The setting we looked at is one that is fully cooperative, partially observable, multi-agent RL. And we're using deep reinforcement learning, as mentioned before, as the strong guy in the back as our toolbox. Right? We also, once again, rely on this idea of centralized training and decentralized execution. Now, the first way you may want to learn messages is by simply doing reinforcement learning, by randomly exploring, by having the sender randomly explore in what messages to send, and then getting feedback from the environment about both the action and the message to learn how to improve the protocol. Right, so this is the sender at the bottom here, that's the receiver at the top. And in the first case, in reinforced interagent learning, they are simply doing trial and error in the space of messages. We talked about why that's bad, because of credit assignment. How can we do better? Wouldn't it be great if there was a feedback signal that comes from the sender to the recipient, informing the sender how to update the message? And that's what we can do using deep neural networks. Because the recipient is a differentiable function, a function approximator that goes from inputs to outputs, the recipient can now pass back the feedback signal, the gradient, all the way to the sender. So this is simply differentiating, backpropagating through the channel. And we can do this because we're doing centralized training, where we have access to all information, including the gradients and so on. So in some sense, now rather than having to rely on random exploration for finding the right protocols, this sender gets a feedback signal from the recipient that tells it how to update the message to be more informative. And that's just by backpropagating end-to-end across the system. We showed that this can really speed up learning by up to 3x in a simple task. And we also showed that now these agents can learn in simple toy tasks how to communicate and what to communicate. This is this, so I'm going quite fast because I want to go to the interesting parts. This is the sender, and that's the recipient, across two time steps. There's one time step here, and there's the next time step. So the sender produces a message, M1, which gets received by the recipient. And in the simple setting, there's no gradient flowing back, no information going from the recipient to the sender. If we're doing differentiable interagent learning, this message now is a continuous activation, which is sent to the recipient. But then when the recipient calculates its gradients, how to update its weights, it also sends back a gradient term to the sender, which is the derivative of this learning signal with respect to that message. So that's how to make the message more informative. And now when the sender updates its weights, it can include that gradient.
And the recipient is learning at the same time.
Everyone is learning at the same time, exactly. Yeah. So we're now doing end-to-end differentiation to learn communication protocols. And we really showed that this can help, and this has now become sort of what people commonly do. Yes?
Are there concerns of like explosion of information that has to be going back and forth? Because if you're going to send these gradients back, that's a lot of, if you have a big model, that's a lot of information.
To be clear, I only have to send back the information across the channel. So that's, if you have a 2-bit channel, that's two numbers. Right? It's only the partial derivative of the total error with respect to this incoming activation. So that's as wide as your communication channel. And I'm allowed to do this because I'm doing centralized training. Right? So when they're actually executing the policy in the real world, they can't have this gradient. But they don't need it in because we're assuming they're done training at that point. These are fantastic questions, by the way. So thank you for that. So we showed this works. Now,
So the messages aren't discrete.
oh, So I photoshopped this. In the original paper, this is a fantastic question as well. There was a box here, the DIU, the discretized regularized unit. So the messages are discrete. And we had to do some smarts here, reparameterizing da-di-da-di-da, to force the protocols to learn something that is at the end discretizable. So we basically ended up learning by modal distributions here with a way of regularizing the channel. I didn't want to go into that detail here, but now we have it. So this was before people did gamma softmax and concrete distributions. It's one of the first papers that actually learned discrete activations using continuous gradients. So this all works, but did we really solve communication? I think we did with communication what Alexander the Great did with the Gordian knot. We had this interesting challenge, this entwined little problem that is about beliefs and points of view, and then we just hacked through it by mapping it into something that we do know how to solve, and that is backpropagation. But there's issues with this, because for a start, it misses the entire connection about beliefs and points of view, which is why we want to study communication in the first place, partially. It also is only applicable when we have cheap talk, when the messages we're sending can be modeled as continuous activations because they don't have any impact on the environment dynamics later on. And lastly, there's one more problem here, which is about local minima. To understand the last problem in a bit more detail, let's fill in some blanks in this sender-recipient game, where the sender now wants to communicate one of three objects to the sender, to the recipient, and the recipient has to go and buy that object. To make it challenging, we're only making a 1-bit message available, so the sender has to map each of these into either 0 or 1, and the recipient then has to decide what to buy. Now, here are a few good sender policies that we could be thinking of. So for example, here's the strawberry sender. This sender policy encodes the strawberry with a 1 and encodes other options with a 0. Now, if you know that you've talking to a strawberry sender, as a recipient, you probably want to buy the strawberry whenever you see a 1 and buy something else when you see a 0. Here are other good policies. The lemon sender is going to encode the lemon, and the nut sender is going to encode the nut. Now, let's look at these tables. Am I missing any good policies? What about mixed protocols? What if a sender encodes the strawberry sometimes with a 1 and sometimes with a 0? That's clearly inferior, because we're going to add uncertainty to the recipient. Clearly, the best protocols here are ones that reliably map one of the inputs to one of the outputs. We'll see that idea later on again. Right? But something else happens. What if we now assume that nuts are a bit more valuable because they are scarce or because we had a drought here in Southern California? Then this pair of strategies where the sender encodes the nuts and the recipient decodes the nuts gets the highest reward. But what happens if during learning the sender switches to some other strategy? Then you get a mismatch. Right? And what this means is, if during training the sender and recipient have ever agreed on any protocol, so for example, if they're encoding lemons with a 1 and understanding 1s to mean lemons, this is an inferior strategy. And yet, a unilateral change, if I as a sender or you as a recipient move away from this protocol to the superior protocol, we get a reduction in reward. Technically, what this means is, if we are learning using exploration in action space or gradients, how to send and decode messages, this has a large number of local minima. These are all Nash equilibria. So going back to game 3, if you're solving for Nash, those are all Nash. Right? So being here is Nash equilibrium, that's Nash equilibrium. Given that sender, I should decode it like this, and I can't get out of it. But humans can get out of this. And actually, one second, yes?
So here, the setting is a little bit different from the introduction, because here, the agents are collaborating, right?
Yeah.
And so they're not opponents.
Yeah.
So does this change the problem? Does it make it easier?
It means that there even is a problem. So if this was a zero-sum game where they are typical opponents, then you don't want to send information. Right? So there's a pretty general statement in 2-player zero-sum games, I don't want to communicate with you. Right? So this is where this problem arises. And a lot of this talk now will be about the challenges. Typically, people think of games that are adversarial as being harder. In reality, cooperating and communicating is a much harder challenge from a game theory point of view, because we do have these large number of Nash equilibria. Right? So here we'll actually get stuck all over the place. And you can see this in the real learning dynamics of the game. So here, we're looking at the PCA plot of 2 agents learning to communicate with each other. And you can see that there's this large number of local optima that they run into, where they just get stuck. Right? So the coloring here is the red is the highest possible reward, and that's the only global optimum. and only a few of the runs actually get to that global optimum. Most runs get stuck at these equilibria, which is when you and I have agreed on any strategy, that implicitly we're stuck at that point. Now, humans obviously can get out of these situations. We can communicate, and we're not stuck in some crazy local optimum. Our intuition was this has to do with beliefs and has to do with the ability of reasoning over the intentions of others. In the recent paper, we explored this. So this is currently under review. Imagine that you are cycling down the road, and you see that there's a person next to a bus stop raising their hand. What do you immediately know? You know there must be a bus behind me. And that's because I can ask myself, why would that person raise their hand next to a bus stop? It's that kind of ability of switching perspective and reasoning over the intent of another agent that we commonly call theory of mind. And it's not just that we can interpret the actions of others, we can also act in a way that is interpretable and informative when observed by other agents. And wouldn't it be great if we could test this in an environment and then develop methods that have this ability for machine learning? That's exactly what we did. We looked at a setting that no longer has cheap talk channels, but where instead the agents have to communicate through their actions. So much like a car has to be interpreted in traffic when observed by others, we now have to communicate to each other by you interpreting my actions. We did this in a card game called Hanavi. Quick show of hands, who's heard of the game Hanavi? 1, 2, okay, fantastic. So this game is a cooperative card game, which means everyone plays together as a team. And the twist of this game is that players want to build these piles of cards called fireworks. However, each player can see the cards of other players, but not their own. This means for me to know what card to play, I have to receive information from the other players. And the main way of doing so is by having them interpret the intent behind my actions. Now, they can also give ground hint information, but that's costly. The main way to get information across is through interpreting the intents of others. So something that would happen in Hanabi quite commonly in human gameplay is I can't see my cards, and then one of my co-players tells me, hey, Jacob, your third card is red. Now, this card being red doesn't tell me anything a priori. What does a red card mean? Like, I don't know if I can play it. However, the fact that that player chose to tell me this and nothing else going on probably means I can play this card. Why else would they tell me? Right? We assume intent. Wouldn't it be great if we could do the same with our machine learning agents? We believe that Hanabi is the next great frontier for machine learning research. Right? Clearly, recent progress has been focused on two-player zero-sum. Find the Nash equilibrium and you're done, go home. Right? But the world isn't all competitive. Humans cooperate and communicate all the time. Clearly, our agents of the future will have to have those abilities, reasoning over the intent, points of views, and so on of others. And we think we can test this in Hanabi. A bit more details about the game. So this is shown from player zero's perspective. So they can't see their own cards. They can see everybody else. And then there's a bunch of stuff happening here. Those are the piles of cards we're building, the fireworks or the stacks at the top. Right? So that's basically what Hanabi is about. But just remember, it's about intent and beliefs and points of view. We're not the first people to look at this. So there have been a number of people trying to write good bots for Hanabi that incorporate the human conventions and search and whatever we can do. And they've reached around 23 to 23.5 points in recent years. The best game you can ever play is 25 points. That's 5 stacks of 5 cards each. That's 1 point per card. I'm not showing, by the way, previous learned methods. This is hand-coded. These are heuristic search methods. Previous learned methods are about 2 meters below the floor at 12 points average. These methods reach around 50-something% perfect games. Right? Now, what does it mean to interpret the action of another agent? And this is probably one of the most important things we can get across here. Because Alice can see Bob's hand, and because Alice then decides what to do, Bob can form a posterior, a Bayesian belief about what Alice's action means about his own hand. Right? So this is the probability of Bob holding a given hand conditioned on the action of Alice is nothing but the Bayesian belief. And if you want to see a brief reminder of Bayes' rule, it's down here. Right? Now what's important, because we're in centralized training, we're allowed to substitute in for the probability of Alice's action, UA, given the hand of Bob, with the policy of Alice. In centralized training, I'm allowed to have access to your policy. And I can actually carry out this belief in principle. Now, what's interesting about this is that in reinforcement learning, remember we had S prime is drawn from P of S and U, conditioned on those two things. If we now think of this belief as being part of the state of the world, then suddenly this belief, yes, it does depend on the action taken, but it also depends in the denominator on the entire policy, on whenever this action would have been taken otherwise. So we fundamentally change the reinforcement learning problem here, where suddenly it's no longer appropriate to just think about actions conditioning the next state. We have to think about entire policies conditioning the next state. And that's effectively why everything else failed earlier with the local optima, because we have to explore in the space of compatible encoders and decoders. And this is simplified, because clearly, if I'm going to have a belief, I should also use it in my policy. Right? So now Alice also has a belief over her hand, and now clearly Bob, when carrying out this Bayesian update, needs to feed that belief of Alice into the policy. Bob doesn't know Alice's belief, therefore I have to have a belief over belief. And what is this? This is another one of these explosions. Right? Because immediately when I'm carrying out this Bayesian update, I have to reason over your belief and you over mine, and that leads to the circle. There have been previous attempts of solving this. It's called interactive POMDPs, where we model these belief over beliefs. But they are intractable, they're extremely hard to do, even for small cases in nested, even for finite nesting. Instead, we'll do something else. We will be using common knowledge here to get around this recursion. Common knowledge are things that everyone knows at infinity. It's one infinite recursion that we can use off the shelf. In particular, in Hanavi, there happens to be everything that is on the game happens to be observed by everyone. So these are all public features, we call them FPub. These include the state of the board, but also include the last actions. The only things that are private features are the hands of the two players, because they're observed by some of the players, not everyone. That's called FA, the private features. Now note, common knowledge, yes, it happens here, but it also happens to be extremely important for human coordination. Humans typically try and establish common knowledge. For example, eye contact is a form of common knowledge. I can see that you've seen me. Right? We also establish common knowledge, for example, in messaging threads or in large announcements at companies. Right? That's all a form of having common knowledge. And what we're going to do now is to get around this circular issue. Instead of modeling two private beliefs that condition on the private observations, we'll have one joint public belief that conditions only on public information. So what this means in Hanabi is very simple. We condition a belief over the private features that is computed only using the public information. And because it conditions only on public information, if you can agree on a protocol, then all agents can compute that same belief consistently. So I no longer have to reason over the belief. Now let's make it specific. This is all quite abstract. This is what the belief actually looks like. Right? So we're going to list all of the different hands that these two players could be holding in a long line, and then we assign some probabilities to them. Right? It's a long vector of probabilities across all the joint hands. Now let's talk about that last challenge of local optima. Right? We want to do two things at the same time. Because we're doing reinforcement learning, I want to be exploring. I have to take random actions to explore things about the world. That's that little explorer icon that I have here. But I also want to have a deterministic policy because that's the most interpretable, as we saw in that like small game. Deterministic protocols are the least noisy and the most interpretable. So how can I be exploring but also be deterministic? The key insight is I need to be deterministic only in the mapping which goes from hands into actions. That policy, because that's what goes in the Bayesian posterior. Right? That's what I'm evaluating. So we'll have a two-step process whereby, first of all, we introduce this little guy here, Pipat, which is a deterministic mapping from private observations into actions. In Hanabi, that goes from the hands of Bob into the actions of Alice. That's deterministic. There's no noise. To explore, we'll be sampling this mapping from a distribution over deterministic mappings that's conditioned on the public information and parameterized by some weights theta. That's our actual policy. Again, abstract, so let's make it specific. This is what PyDet looks like. Our list of instructions is this mapping from hands into actions. So it's a long vector that assigns an action on the right-hand side for every possible hand of Bob. It instructs Alice what to do for every possible observation. You can also think of it as being a function that takes in the private observation and returns the action to it. And what is this Pipat, this distribution over actions, over maps, right? This is a probability distribution that assigns a probability to every possible deterministic map. That's what we're sampling from. This is where we do the exploration here. Right? Importantly, in different situations, I want to have different maps. So therefore, this takes as input the public state, this BT, the public belief and the public observation, and it's parameterized by some weights theta. That's that mapping which tells us what's the distribution for every possible state. Now let's look at the Bayesian update, right? Because we had this idea we have to do a Bayesian update here. Right? So we had some previous belief, BT, which are all the possible hands. Then we know the deterministic map, what happens in every possible hand. And now we know the action that actually took place. So all I have to do is I have to ask myself, in this hand, what would Alice have done? If Alice was observing this hand of Bob, what would she do? We can look it up here. Well, she would play the fifth card. It's not what happened in reality. That belief is gone, right? Oh, let's look at this. What would Alice do if Bob was holding 5 5s? Oh, she would discard the third card. What happened in reality? Alice discarded the third card. That belief is still viable. Right. So that's how Bayesian update works. Now you just have to renormalize it. Now, if you put everything together here, if you believe this can be done, then we get this following picture, whereby we now have a new state that consists of the public belief and the public features. We're going to sample a deterministic map, indicated here. We'll evaluate it for the current observation, only the acting agent. We'll announce this action taken to the environment. It's also observed by everybody else. The environment goes to a new state, and then we decode the message, if you want, the action using the Bayesian belief. That's the receiving part here. This did something quite radical to our problem. We started out with a partially observable MDP, where we had some state, we had private and public features. This MDP, it's partially observable, it's multi-agent, and we have all these issues we talked about, local minima, communication, and so on and so forth. This is the new lay of the land. We've arrived at a new MDP, the public belief MDP. In our representation of the problem, the state consists of the public features and the belief. That's not part of the state. We're now acting by writing down entire list of instructions. Every time we're taking an action which is sampled from this policy up there, we're writing down what to do in every possible state. It's a new action space. The action space consists of all deterministic maps. Next, the action is evaluated by the environment. We get to a new state, new features F pub prime, but we also get a new belief, B prime. And this belief doesn't just depend on the action that was executed. It depends on the entire policy of what would have been done in every possible state. Now, why is this nice? This is now a Markov process. This is now just an MDP. In this formulation, if we are willing to act in the space of deterministic policies, of writing down entire policies, we can now in principle treat this as a fully observable system, as a single agent, fully observable problem. And we can now, if we can solve this, the technical challenges, we can now represent any of these problems as a fully observable reinforcement learning problem that can be solved with feed-forward neural networks, single agent. So we've radically changed the representation of the problem by going through these beliefs and using Bayesian updates. And this can in principle be done if you can do all these parts. There's a pretty general formulation of the, if you can do what I said you have to do. Because we'll go into the details now of why this is actually really hard, and then we'll blast through how we solve them, and then I'll tell you more about the future. Questions?
So in the public knowledge part, nothing can be
Yeah, so that's a great question. So the belief update, right? Can there be any sampling here? Can any of this have noise? It can't, as long as you are, first of all, agreeing on the source of noise. And that will play a big role in how we actually do this in reality, right? We can have noisy policies as long as we pre-agree on a source of noise, which is like humans agreeing before the gameplay on a set of conventions. This is what we'll try out in this round of Hanavi. More questions? This is, by the way, if you can understand this slide, then I think you got a lot of the why this is cool. And then in the next, I'll just tell you why it's hard and how we solve it. And then I show you it actually works. But this is really, like, conceptually speaking, this is the cool part, right? That you can get to a new Markov state here and having an action space of entire policies that we think about. Good. So now let's talk about the mechanics of this problem a little bit. Right? Because everything so far was like we have these beliefs and we have these Bayesian updates. This is actually really, really hard. So for a start, the belief is 6.2 times 10 to the 13 entries, even for two-player Hanavi, right? You're not going to write this belief down. You're not going to represent it. You're not going to do the Bayesian update. Secondly, our deterministic list of instructions has 9 million entries, right? This is actually 9 million long, so it also goes like pretty far down below the floor. And if those are large numbers, let's think about the distribution over deterministic maps, right? How long is this x-axis here that we're thinking about? That's 21 number of actions to the power of observations. So 21 to the 9 million. Right? Surely if you factorize, it's 21 times 9 million, but I think you're still in pretty bad territory here. And we managed to resolve all of this. The first thing is quite obvious. What you're going to do is don't represent beliefs over joined hands, represent per card probabilities. Right? So what we've done is we've gone from this long list of instructions to an array where each card is assigned some probability of having a certain value. There's 5 colors, 5 numbers, 25 entries in every of these columns, and we have 10 columns in total. 5 columns for Alice, 5 columns for Bob. Now, this is a terrible idea because you throw away all the information of interactions between the cards. You don't want to do this, ever. Bad idea. Right? Because if you think you're holding the yellow 5 here, you shouldn't also think you're holding the yellow 5 here. So we found a way to fix this. Details are in the paper because I'm running a little bit out of time, but we call it the iterative self-consistent belief update, where we can fix some of these interactions by looking at the beliefs we have in other positions of the hand, capturing that effect. Secondly, let's look at the Bayesian update here. Before we had the summation, it turns out we can do a sample-based Bayesian update from the factorized beliefs by sampling joined hands and then remarginalizing in one go. And that's happening here. So here we're just sampling from the joined belief, which is factorized, and then we're remarginalizing, this marginalization happening, checking if the feature matches that specific feature of that card, and just checking whether the action that would have been taken in this hand matches the action that was really taken. And we do about 3,000 samples. And because we're sampling from the joint belief, we're sampling from the head of most likely hands. This actually is enough during our training process. Now let's get to the most hairy part, which was the 10 to the 21 to the 9 million vector I talked about. And that's the distribution over deterministic policies. So just to be clear, we're trying to learn a mapping which takes as input the public state, S bat, which are the beliefs and the public observations. It used some weights theta to map into a distribution over deterministic policies. Right? That's the task at hand. Sounds quite daunting and scary, because I never want to write down a neural network that has 21 to the 9 million outputs. And neither should you. It's a bad idea. Instead, we'll start out with a feed-forward neural network. So this is one of our big function approximator things that we had. And this thing will take as input 2 things. It takes as input the private observation and the public state. It processes it and maps it into distribution over actions that the agent can take. That's our starting point. Now let's consider the following. What if I fix the public input? Consider this as given. What did I just do? I just established a mapping from private observation into probabilities over actions. Interesting. So for every S bat, I now have a map from FA into probabilities. It's almost what I wanted, no? I wanted a mapping from FA to action, a deterministic map. But here I have a stochastic map. I have something that assigns a policy to every possible FA input, simply by fixing these other inputs. Now, how do we go from a distribution to a deterministic action? I want one single action to be assigned to every FA because that's my deterministic map. And I want to get there randomly, a sample process. If you ever want to get rid of randomness, condition on the seed. Right? If that's your problem you're facing, what you're going to do, you're going to sample one seed, xi, right? And that seed is just some integer. And this corresponds to sampling the entire map pi det from the distribution. And that is because once I have this seed, then I can now assign a unique action to this distribution. And that's when I sample from P of U given FA, which was this map we had before, but conditioning on the seed xi. Because the sample process, if you fix a seed, is deterministic. And that's our way of producing entire maps that we can sample from a distribution. So this induces a distribution over deterministic policies. And that's what we map into. So our pi det of FA is nothing but a feed-forward policy evaluated for a given S bat with this FA, and then sampled from using the seed xi. That's pre-agreed by everyone else. Questions? Yes? We're going to fix the seed, and all we need to do is that you and I, when we're evaluating the distribution to sample, use the same sampling process.
Do you see anything about the way your sampling process uses the seed?
No, I don't. There's no bucketing, there's no further assumption apart from the fact that once you condition on the seed, the sample is deterministic. And that you and I can use the same program to evaluate this distribution. There's no more smoothness assumption. I'm not assuming that the sample processing is smooth in Xi, for example, or smooth in the inputs. I'm just assuming that together with the distribution and the seed, the sample is deterministic, which is the definition of pseudo-randomness. Right? This is going to run some deterministic program that once conditional on the seed, the randomness is gone.
Is this a version of Pegasus then?
If you don't mind explaining me more about what Pegasus is.
Handerin's reinforcement learning algorithm that fixes the random number generator so that the sequence is deterministic and you can repeat that.
No, it's not, because the randomness of the environment lives separately, right? So there's still true randomness going on in the environment here. So this is just a means for us to explore in the space of deterministic policies. Right? And what's important here is I have to be deterministic in FA because that's what's going to hit my Bayesian update. Right? I never want to be in the space of noisy policies because they won't have informative posteriors. Right? So through this, we can sample from an induced distribution over deterministic maps. Good. So now this all sounds a bit crazy. We're doing this approximation. Does it actually work? The answer is yes. So in a nutshell, these are previous results, and we are at 24.2 points using all of this machinery in this new benchmark Hanavi. And we beat everything that had been done before in the game, including learning methods, hand-coded bots, and so on. We also get around 60% perfect games. So these are now bots that are playing in a way that is probably superhuman in this theory of mind game that Hanavi represents. We can also look at some of the learning curves. So here you can see that not only the red line is our method, we learn faster than our baselines, which are extremely strong, but we also get higher performance. If you wonder, why is there this red dashed line final performance higher than the red line during training? That's because at inference time, we can actually run more samples in the Bayesian update. So that's something nice about this method. During training, we need billions of samples. But at test time, we're only playing this game, 100,000 times to get good scores. So then we can be more expensive. I think having methods which can do more expensive work when deployed in the real world rather than doing training is something quite interesting. Because then you can amortize your training and really put more resources behind it when it counts in the real world. This is a histogram, so the bot gets low scores very rarely. We sent our bot to the writer of the Fireflower, so a Fireflower bot, and asked for commentary. And first of all, there's a few things that come back from this. Some of the conventions this bot uses are very human interpretable. We didn't tell it anything about playable cards or human conventions, but it so turned out that when the bot hints for red or yellow, it means play the fifth card, the newest card. It does something similar with white and blue. Now I'm just going to cite David Wu here. The bot is very strong in the early game, and their convention set is overall far more efficient than natural human convention sets. It's really quite beautiful. So this was quite a nice thing to hear from somebody who'd been thinking about Hanavi for a long time. Right? And just be clear, this was all learned up in issue. There was nothing fed in as prior knowledge. Now, this isn't all I've done in the last few years. I've done a number of other papers. In one of them, we did address this credit assignment issue. So counterfactual multi-agent policy gradients was published at AAAI and received an award there. This paper was also used by AlphaStar. So I don't know if you saw the StarCraft 2 results. This idea of centralizing the value function during training, which is only needed in the centralized training phase, that was used by the StarCraft 2 folks quite successfully. We looked at the non-stationarity that happens in multi-agent settings. And I also did some work on gradient estimation, creating new objectives that we can use to generate policy gradient estimators, including high-order terms. Basically turning reinforcement learning into a supervised learning problem, where we have one loss that has arbitrary order gradients that you can optimize over. This is, and then there's another paper I was involved in here that was an offspring of Lola, which is this mechanics of M-play differential games, which received a reward at ICMA in 2018. Now, this has basically been my work up to date. Now, do I think I'm done with my agenda? No. I think we're just getting started here, right? Because there's a lot of things that I hope to be doing in the next few years. One of them is to move away from self-play, go from bots to humans, right? That also ties in with the idea of making it real, like how we can get me something out of card games. And then lastly, concepts and theory, because Nash isn't really the right concept out of equilibria, right? Away from equilibria. The world isn't in equilibrium and probably will never reach equilibrium. So how do we have a general theory for learning systems? For the first part, from bots to humans, I really think of this work so far, how do we learn good value functions, as being a great test bed for exploring ideas of agency in learning systems. But it's clearly just one first step. As a next step, can we move away from this and move towards settings where we have to cooperate with unknown bots? What if we can do this? Maybe we can cooperate with humans in the loop. And lastly, what if these humans are learning? What if they're adjusting to our policies? How do we get there? Well, as a first step, what if I could learn in self-play to create a diverse set of final policies? Just creating diversity in our training population. Right? Training and population-based training and playing with the different levers. For example, I could incentivize the orange agent here to try and find a policy that does great in self-play, but that the blue agent can't play with. Right? Now, this is cooperative, but still I want to find a different policy from the blue agent. What if I can use other sources of diversity, such as hyperparameters, learning algorithms, discounting? What if I could even learn distributions over agents and sample and generate new agents from there? What's the point of all of this? Well, if I have this diverse population of agents, then maybe I can learn one agent that can be dropped into a team of any of these diverse agents and quickly learn to adjust. And because I'm still using bots, I can use billions of samples, assuming I have the compute. Right? I can put money on Moore's law and hope that the compute's getting cheaper. Human labor won't get cheaper, compute will get cheaper. And I can train these meta agents to adjust quickly to unknown teams. To do so, obviously, we have to do a lot of smart work around opponent exploration, opponent modeling. Thinking about the beliefs, incentivizing discovery of new strategies, understanding what's happening in these agents. But we can do this because it's centralized training. I can have ground truth access to the beliefs of my opponents during training, as long as I can then generalize to an opponent during execution time and model those beliefs. So obviously powered here. Next, what's the point in doing all of this if the policies that we are generalizing to happen to be far away from human policies? So we want to be able to nudge policies in self-play to end up somewhere near the space of human policies. Right? And there's things we can do again. So we can shape the rewards. We can think about having some nudging factors like cross-entry penalties with humans in the loop. But there's also specific things we can do about limiting information access. So in Hanavi, we know that in humans almost discard negative information. If you tell me this card is red, you're also telling me that these cards aren't red. But humans ignore that fact. So if we hide that information from our agents, do they then learn more human-like policies? We haven't tried that. Right? There's a lot of levers here, and this is an area where we love to collaborate with a lot of people who are looking at psychology, at cognition, at human-robot interaction. How can we think about our learning mechanisms and try and nudge them in a way that makes the self-play policies resemble more of human-like policies? And then obviously, for me, it's always at the end about learning, so going from humans in the loop to having learning humans in the loop, right? And that's a bit of the progression earlier, like I have a Lola agent that models the other bot as a naive learner with access to the weights. Then the Lola agent models the naive learner without knowing the policy. Can we then, at some point, model a human learner in the loop? Well, the good news is, in the previous step, we learned a lot about the rewards that humans might be optimizing, the learning algorithms that might be running there. Right? But again, another area of great collaboration here, building these different building blocks. Clearly, doing card games is great and fantastic, but it's not what we really want. Right? I believe these questions of theory of mind and beliefs and points of view matter in traffic. So can we go from a board game to a simulator that focuses really on these questions of agency? That doesn't just think about pixels and driving directions, but thinks about interesting situations where we have points of views and multiple agents and beliefs, where we can carry out centralized training. Another area where I hope to collaborate, and I think UCSD is a great place because there are a lot of people interested in this question of self-driving cars, and how to interpret the actions of drivers and of pedestrians. Right? But we don't really have good tools to simulate these questions of point of view and belief. Right? If I can see that driver and they can see that driver, what does that mean about the world? Obviously, in the long run, 10 years out, you're going to go to full-on simulations and real-world data. Another thing that would be exciting to do here, if we have all these great models of learning agents, can we start understanding social systems better? So we did some work on fake news in social networks, where we modeled agents in social networks as RL agents that try and maximize information gain. We could understand some of the spread of fake news. But really, technology has been a great source of disruption so far in the last few years. Can technology and our methods also be a source of stability? understanding better how emergent phenomena occur in systems that have millions of agents. Right? Can we understand how fake news spreads, how misinformation spreads on social networks? Yes?
How smart do you think the agent has to be, like, in order to model this sort of system?
It depends a lot on what you're trying to model, right? So I can, if we have another 2 minutes, then I can tell you a little bit about what we did in our fake news paper. Basically, in that setting, we had a simple, very simplistic model whereby there was a simple signal about the world that was either true or false, a binary variable that's true or false. And the task of the agents was to try and understand if that signal is true or false. Now, all they had was their local observation, which was a noisy version of that variable. But they could also see what their neighbors are thinking in the network. And then we just trained a deep reinforcement learning agent to try and guess the right thing. And even in this very simplistic setting, we could show that as an adversary, if you're trying to perturb the opinion of this network, giving you access to the network structure increased your abilities of causing disruptions. So if you want to model like full-on social behavior in a true social network, these agents would have to be very, very smart. But I don't think that's always what you want to model. If you want to understand more of the instability and the emergent dynamics, just to be clear, some of the models economists are using right now are extremely simplistic. They're linear models, right? They are often assuming optimality. So anything we can do on that front, I think, would be interesting and appreciated by the community. Because these can be powerful models if we train them properly. And all we've learned so far in the last few years is how do we train multi-agent policies in simulation. Yeah. And then lastly, I talked about this conceptually, right? So Nash was a great way to get around circular thinking. But in some sense, we have to move away from Nash because the world isn't in equilibrium. We are learning and updating, and we don't know the optimal policies, let alone are we able to play them. So, this question occurred earlier, is there a fixed point? Right? Can I go from a Lola against a naive learner to Lola 2 against Lola 1 to Lola infinity? Because that should be the fixed point. If all agents are infinitely aware that there are other agents that are also learning. This is an unknown question, nobody knows, right? So this leads us sort of to the final grand idea here, which is, can we take this recursive thing that happens in multi-agent systems, which has so far been a great source of disruption and of conceptual struggle, can we take this recursion and harness its potential by developing a general theory of agency in learning systems, right? Where this now doesn't disrupt the world, but it becomes a source of inspiration and of innovation and of novel applications and insights. And on that journey, yes, we made a lot of progress on how to train multi-agent systems in the last few years, and we've got new benchmarks. But in that greater journey of moving towards a real understanding of agency, of ourselves, of points of views and beliefs, on that journey, I think we're just taking the very first steps now, and I'm quite excited for the next 20 years to come. So with that, I'd like to thank you for listening and open the floor to questions.
Thanks for a great talk. One thing that I'm really interested in, as soon as you start talking about communicating with natural language in a multi-agent system, there's kind of a lot of overlap with this and the linguistic study of pragmatics, and that might even give you a lens for interpreting some of your results. So I wondered, have you seen anything in these trained multi-agent systems that you could say match, for example, Grecian maxims or something, or have you used other tools to look at that?
So just to be clear, I think this very idea of reasoning over the intent of the sender, let's go back to the very first slide here. This really is a pragmatics, right? This, in some sense, is the first step of a pragmatics loop, right? Where you assume an informed sender, and an informed receiver assumes an informed sender. So absolutely, this is very close to pragmatics. The difference is that in pragmatics, as I understand it, typically you're giving the symbols and the meanings and now trying to use them most efficiently in the context. Versus our agents that have to develop the meanings themselves. This is not grounded. The fact that then the fifth hint, like red means play the fifth card, right? That wasn't fed into the system. And this wouldn't come out of a pragmatics approach, as I understand.
Well, language itself has evolved through presumably a similar approach. So you can think of kind of the study of pragmatics as a way of interpreting the results of that learning process.
Yes, 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 yes.
I just think it would be really interesting if you went back and looked at your parameters
Yeah.
and you saw, for instance, oh, it learned to communicate using these principles of communication because that was efficient.
Yeah, I think that would be a great thing to try. We haven't had time to analyze this. All the data of the gameplay, so you have 300 gameplays online, and you can see how the beliefs develop over time. It's actually quite interesting. If anyone you want to spend, waste a lot of time at some point on something you didn't intend to, go and click through the paper and look at the games. It's quite fascinating what happens, and you can really see how beliefs move. One difference maybe between the typical setting of pragmatics and what we're doing here is information isn't equal to information here. Commonly, these agents will induce false beliefs in listeners. They will take actions which will result in a person thinking they're holding a different card. But that is terrible from a pragmatics point of view because not being informative. But in this game, as long as I can confidently believe you're going to take the right action based on that belief, then that's perfectly fine, right? So they will actually induce false beliefs, which is also something that's known in the Hanavi community. It's called a bluff. In Hanavi, you commonly try and make somebody else believe they're holding a certain card because that's easier to communicate. It might be easier for me to tell you that you're holding the yellow 5 and that that's playable, than to tell you that you're actually holding the yellow 3, which is also playable, as long as I can be confident that based on the belief we'll take a certain action. And this is something that we also find in these agents.
Quick follow-up question.
Yes.
Also related to language.
Please.
So I think that's it's a great idea, kind of moving this to kind of more realistic settings and starting to think about putting humans in the loop. I just wonder if you could speculate a little bit about how you might actually incorporate kind of free-form language as a signal in here. Have you thought about the difficulties that come up with that?
I think, I think if we think about the 5-year horizon, 10-year horizon, I'd probably stay away from free-form language for now. But if we're willing to think about 20, and research is all about long-term horizons, then absolutely, right? So at some point, I do believe there's going to be a mapping that it probably won't be trained end-to-end, right? But like having some abstract state representation first, that the agent can act over and can act in, and then having a second system that maps from these abstract states into natural language, right? I think there's got to be some intermittent phase that takes out some of the complexities. I don't imagine we'll have an agent that goes around and tries to babble random words and then learns by interacting with humans how to speak, right? I think at that point we want to combine everything we have, be it semi-supervised, be it language models, be it linguistic experts, put everything together, and then some part of that in that pipeline at the high level will be about reinforcement learning, right? Where the agent basically then thinks about which communication actions to take and what's the state, right? And there's already some work in that area happening right now. There was an interesting paper we talked about earlier in the meeting, which was about negotiation using natural language and reinforcement learning. And they found that having this reinforcement learning part, which is sort of about state keeping and trying to push towards a certain target outcome, helped a lot in that case.
Thanks.
Well, thank you for the questions. Thank you.
Is there any place for symbolic reasoning within this framework, or is machine learning always the best approach? So for example, you could easily specify traffic rules or physical constraints symbolically, rather than having to learn them, which seems much harder.
I mean, I think it's similar to what I said earlier. In the end, any successful system applied in the real world will have components that consist of hard-coded rules, safety, and so on and so forth, symbolic reasoning, but also there will always be a learned component because we did learn over the last 20, 30 years that we can't encode everything in hard-coded rules, right? So I think in the end, it's sort of another axis of great challenges for machine learning or for AI research in general. How do we combine symbolic reasoning with learned differential methods, right? And we actually touched upon this a little bit here because we had this discrete message which we learned by backpropagation. Right? So how do we mix symbolic things with optimization? And I think it's a great challenge. I think this is also all great challenges, but there's another great challenge right there. And they're not unrelated because if you think about agency, I want to think about abstract representation of others because I can't represent another agent as the same complexity that I am, right? My brain clearly can't represent your brain and vice versa, I hope. So there has to be some abstraction, right? And agency immediately to me gets towards abstraction, which gets towards symbolic reasoning. And I would also be interested in if there is direct approaches here of combining those things in the context of multi-agent settings. More questions? Yes.
So in this card game, it seems like you're learning a protocol, but your language capability is restricted by certain
Yeah.
things you can do, right?
Yeah.
Do you think in a real world setting it'd be better to, or how different it would be to just have unconstrained ability to communicate?
Well, so I mean, in this card game, that would destroy the point of the game, because then you could just play open-handed. Actually, I take it back. Even then, it's still a hard game. Turns out it's like NP hard in some axes, even if you can see all the cards. Fun fact about Hanavi. But it's not the point of the game. Humans, in any setting, we don't have unlimited bandwidth, right? And it wouldn't be the right thing. Like if I just, instead of being here, showed you my brain scan to full resolution, right? You wouldn't be any wiser from that. So communication constraints between agents also have to do with the computation constraints of the recipient. I can't just dump my brain for you. So there's a natural place where communication with limited bandwidth has a role to play in the world. One of those places is when it's not cheap talk, but when we have to interpret actions of others, like in traffic, understanding the body language of a cyclist, of a pedestrian, of a car nudging, right? They'll be around. There's going to be organic traffic participants for the foreseeable future. And we have to both interpret the actions, but also understand how we can be interpretable to them. How in my body language, in my signaling, I can be interpretable without cheap talk. And once again, I can't just give the pedestrian the source code of the self-driving car and be like, figure it out. Right? It wouldn't actually help to have an unconstrained channel of communication. What you communicate is still a question. Yes.
I have a question about supervised, which is we're making structural assumptions about the world, which is our agents have belief states. But to me, it seems that in many scenarios, what we really only need is predictive knowledge of the world that can be obtained in a supervised manner. Like if I see someone driving, I don't need to know that they have internal state. But what I need to know is that they're going to keep driving forward. I was wondering if that's another.
This is actually what Waymo tried. Waymo, to be clear, is a Google company. Google loves supervised learning, right? This is the one hammer they have, and they're going to hit it as hard as they can. And they tried, right? What's the issue? If you just assume this car will keep driving forever, you're not going to get in the lane. Yeah, the prediction is there's a car going at constant speed to your left, and the prediction is this car will want to always go constant speed to the left, right? You'll never get in the lane. You have to think about, did this car perceive me? If I now nudge into the lane, is it going to slow down for me? The answer is yes, then I can go into the lane, right? So simply predicting the world doesn't actually let you tell you what to do in the world of agents that respond. So then you have to start modeling, predicting the response of an agent, and that's much harder, right? Suddenly it's about planning and thinking about how does that agent respond to my action. Well, can you do that without being aware of whether or not this agent has seen you, right? And then it's about really getting to a mechanistic understanding, to something that extrapolates to novel situations. And that's sort of the main hypothesis here. Agency matters because it has explanatory and extrapolatory power. We can extrapolate to novel situations.
Okay, it's been pretty long.
Thank you. Thank you for the questions. Fantastic.